The June 2023 skeleton code program, it's quite complex. It's effectively a assembler for the assembly language, and I'm going to be helping you go through all the functions and how they work and all the subprograms. Right, so there's some characteristics about the program you might want to know before you start going into the exam. So first of all, it can only take around 20 lines of assembly code, and second of all, there's only a set of predefined operations it knows how to do. These are the operations that are on screen right now. Honorable mention to one of the worst things I see programs do all the time, which is shortening the names of their constants. Now this doesn't seem bad because you don't have to type out as much when you write them out initially, but this is really awful, especially when you get down to really large programs like this. For example, as a person who didn't write this code, what do you think TOS means, or ERR, or ACC? You have no idea because the variable name doesn't describe it properly. Writing a long variable name isn't that bad. Like, this isn't basic writing computer language in the 1960s on a Commodore. We have a large screen now. Usually it was the case that the screens were very small, so you had to shorten down their variable names. But this isn't the case. You can just simply press tab and your long variable name will auto-complete itself. You don't even have to write it yourself. Right, so we can finally start talking about some of the functions and subroutines running in this program. We'll start from the easiest ones, like the resetting the memory, and then we'll slowly progress to the harder ones. Our source code variable holds the assembly code we loaded in earlier. We'll discuss loading in later. It's important to note that the first index, which is 0, is always the number of lines of code in the assembly file, and every other index represents a line of assembly code. Now we can start looking at the ResetSourceCode subprogram. It first starts a loop from 0 to the max number of lines. High mem is 20, so our max line count is 19. Remember that having 19 as the max index means that we have 20 indexes because we count 0. It fills out every index with an empty string. Right, now that we understand reset source code, we can start learning about reset memory. Reset memory works on a very similar basis, except each piece of data in an index of memory is part of the assembler instructions data structure. Here are the 3 fields of the data structure. One of these names is a bit misleading, but I'll get into that in a second. Opcode and operand string is what you'd expect. Opcode is the instruction, like add or LDA, and operand string is the string name of the register your data is in. Weirdly, operand value doesn't hold the value of the register, but rather the line where the register has occurred. However, calling a register is a little bit inaccurate. In fact, every single register you see here is a label. As you can see on line 16 and 17, num1 and num2 should be registers but are labels that point to 7 and 0. Now this is a little bit confusing, but bear with me. In the first line of prog3, we can see that the operand called is num1. Now num1 is all the way on line 16, so the operand value is 16. In the second line, sub2 is called. Sub2 is on line 4, so sub2's operand value is 4. I'll quickly show you a trick you should utilize to help the readability of this program. When you type 3 quotation marks above a function or subprogram, you can comment it. This is good because whenever you see it being called, you can hover over the call and it will read your comment. Another quick tip is that when you're hovering over a subroutine being called, you can press it and then press F12 and it will bring you right up to the subroutine. There are actually a lot of different display subprograms, and I won't go through all of them here because some of them are quite simple and easy to understand. I will go through some of them that may require more attention though. The first ones I'll go through is display memory location and display source code line. You see the $ and those curly brackets? That's called string interpolation, and it just means we can format our strings nicely. That -5, 3 and -40 is to help the outputs line up nicely under each heading. These subprograms work one after the other. First the program displays the memory location, then the line of source code it's referring to. That's why display memory has a console.write and display source code has a console.write line. It works like this back and forth until the first frame of execution is finished and repeats for the next frame. These subprograms are both called in a subprogram named display code. It first prints out all the subheadings and then grabs the number of assembly lines. Remember, index 0 doesn't actually have any lines of code, so we can disregard this section for now. Then we run a loop for every line of assembly code and call the functions we just discussed. Another important subprogram to know about is display current state. Display current state prints at the end of each frame to show the state of each register, these being our constants PC, ACC and TOS. Each constant has an associated number, which is the index location where that register should be in our registers integer array. A little bit confusing at first, which is why I said not to shorten constant names. You could, for example, add index location at the end of all the register names, and it immediately become apparent what those constants are used for. Now we know about some of the core variables in our program, these being source code, memory, and registers. It's time to start going through the program properly, starting from AssemblerSimulator. This looks scary, but don't worry, it's quite simple. We initialize our source code and memory arrays to be empty and create a flag to turn off the program when it should be closed. We also have an input variable as a char. This just means it will only accept a single character as an input. If we try more than one, our program won't accept it. At this point, we just collect the user's input. We'll start with L, which loads our assembly code into source code and resets the memory in case we have any residual data from previous execution of the program. Here's how LoadFile looks. First, we create a file exists boolean and set it to false. We'll discuss what this is for in a second. Source code is reset to flush out any old data. We create a variable to hold the number of assembly lines and ask the user for the file name to look for. At this point, we reach a try-catch statement. Unless there's an issue with the compiler, the only reason our next section of code will error fatally is because our program can't find the file we specified. That means our code will fail here and not run long enough to change file exists to true. In this case, our file effectively doesn't exist and we get error code 1. If it does exist and some unknown error occurs while reading the file exists would have time to become true, and so error code 2 will print. That's all I'm going to discuss for now. Bye.